Hey, so in this video, we'll be seeing the proof of contradiction. What is the proof of contradiction? Say, if I need to prove that, for example, root 2 is irrational, how will I prove it? Yeah, the one obvious way is to expand it in its decimal representation form, and then you can see that it is neither terminating nor recurring, hence it follows the characteristics of irrational numbers, hence it becomes irrational. But if I don't want to expand it in its decimal form, then how will I prove it? In that case, we will use the proof of contradiction to prove that root 2 is irrational, right? So before coming to the proof, there is a small concept that is based on fundamental theorem of arithmetic that you should be knowing. Say the theorem says that if a square has a prime factor p, right? If a square has a prime factor p, or in other words, you can say that if p is a prime number that divides a square, this implies p also divides a. This is the theorem that is required in order to prove that root 2 is irrational, and the theorem says that if a square has p as a prime factor, that is p is a prime number that divides a square, then p also divides a. Let us see how. Say for example, let us say that a has some prime factors p1, p2, p3, and so on up to pn. Okay, they may be same, may be different, but let us say that a has these prime factors. So a square can be written as p1 into p2 into p3 up to pn, multiplied by again p1 into p2 into p3 up to pn, right? This means a square is equal to p1 square into p2 square into p3 square, so on up to pn square. Now you know that as per the fundamental theorem of arithmetic, each number has a unique prime factorization, right? Each number has unique prime factorization, right? So I can say that the only prime factors of a are p1, p2, p3 and pn, right? The only prime factors of a square will be p1, p2, p3 up to pn, right? And since initially we took the condition that a square has a prime factor p, so I can say that p will belong to either of p1 to pn. P can be any one of them because p is also prime factor of a square, right? But what are basically p1, p2, p3 up to pn? They are the prime factors of a. Hence, P also divides A, or in other words, P is also the prime factor of A. I think you understood. I'll just repeat it once more. Say A has prime factors P1, P2, P3 up to Pn. Now since A square has a prime factor P, this is our initial condition and we need to prove that P also divides A. So let us say that A is equal to P1 into P2 into P3 up to Pn. So A square can be written as its like a prime factorization of a into again the prime factorization of a. So a square is equal to p1 square into p2 square into p3 square up to pn square. Now you know that any number has a unique prime factorization, right? So the only prime factors of a square that are possible are p1, p2, p3 up to pn, right? Now since a square has a prime factor p, so this p will constitute any one of from p1, p2, p3 up to pn, right? But what are they actually? What are p1, p2, p3 up to pn? They are the prime factors of a. Hence p is a prime factor of a. This will be more clear when I'll take an example. Say I have a number 6 square, 36 for example, right? I have a number 36. I know that 2 is a prime factor of 36, right? So as per our theorem, 2 should also be a prime factor of 6, is it? Yeah, because 6 is what? 2 into 3. This is what the theorem says, right? So now I hope that this concept is clear. So based on this concept, we will start our proof of contradiction. So in this video, I'll be taking an example of root 2. The same process you can extend for other irrational numbers also. Okay. So let us say that, since it is a proof of contradiction, we know that root 2 is irrational, but fine. Let us think that, okay, let root 2 be rational. Just now, let us say that root 2 is rational. If this is correct, if our process, it depends on the process. If everything goes fine, then it will be rational. If there goes something wrong, then we'll say that root 2 is irrational. That depends on how we proceed. But as of now, let us just say that root 2 is a rational number. If root 2 is rational, then root 2 can be represented somewhat in the form of p by q, right? If root 2 is rational, you know that any rational number can be represented in the form of p by q, where obviously p and q are integers and q is not equal to 0. That condition is obviously there. But if root 2 is rational, root 2 is equal to p by q. Okay. Now, they can be in their simplest form. They cannot be in the simplest form. They might have a common factor other than 1. So, after division of by their common factors, let us say that root 2 can be written in the simplest form of a by b. Okay. After the division by the common factors other than 1, let us say that root 2 can be represented in the form of a by b. Okay, where a and b are co-prime numbers. They do not have any, I'll write it down, a and b are co-primes such that a and b have no other factor, common factor other than 1. Okay, so this is the first thing. So now root 2 can be represented in the form of a by b. Let us cross multiply. This implies root 2b is equal to a. Squaring both the sides, we get 2b square is equal to a square. Okay, that 2b square is equal to a square. Now here you can see that a square is nothing but 2 into b square. So can I say that 2 is a factor, or basically prime factor, of a square? Right, 2 is a prime number, and here according to this equation we can see that 2 is a prime factor of a square, that is 2 divides a square. Then as per our initial theorem, I can say that 2 divides a. 2 divides a square and 2 is a prime number, so 2 also divides a as per our initial theorem. Okay, now since 2 divides a, I can write that a will be equal to some 2 times another number. Okay, let's see, is an integer. A is an integer, so since 2 divides a, I can write that a is some 2 into c. Fine. So now let us square this again. What we'll get? A square equals to 4c square. This is statement number 2. Now let us put this value of a square in our statement number 1 here. And let us see what we get. So 2b square is equal to a square. So 2b square, I'll just put the value of a square as 4c square. So this gave me b square is equal to 2c square, right? So from here again we can interpret that 2 is a prime factor of b square, right? That is 2 is a prime factor of b square, that is 2 divides b square. Then as per our initial theorem, 2 also divides b, right? This is what we concluded from here, and from here we concluded that 2 also divides a. But what was our initial assumption? That root 2 is in the form of a by b, where a and b are co-prime numbers, that is they do not have any other common factor other than 1. But as per our derivation, as per our process here, we can see that a and b have a common factor of 2 other than 1. Hence, why this problem is coming out? This problem is occurring because of our wrong assumption that root 2 can be represented in the form of a by b. Hence, this is not true. So we can say that root 2 cannot be represented in the form of a by b, where a and b are rational numbers and a and b are integers and b is not equal to 0. Hence, root 2 is irrational. I think you might have understood the proof, and this is known as proof of contradiction. That's all. Thank you.